Hey buddies, today we are going to solve another daily LeetCode challenge, problem number 743, network delay time. So in this problem, we are given a network of n nodes labeled from 1 to n, and we are also given the times in a list format, and the times are the time that it takes to transfer a message from a source to destination. So if you take a quick look at the example here, so given a node, so here we are given a network of 4 nodes and a list of edges, and for each edge, for example, the time that it takes to transfer a message from node 2 to 3 is 1 second, and from 2 to 1 as well as 3 to 4. And we are asked to find the time that it takes starting from a node k. So for example, if in this case k equals 2, so if we are starting from 2, the time that it takes so that we transfer a message from that starting point to all nodes, all other nodes. So in this case, after 1 second, so the message will be transferred to the 2 has already messaged, node 2, 1 and 3 will be having the message after 1 second, and after 2 seconds, so the message will be reached to 4, and then so the minimum time would be 2. But in the same network, if we were starting from node 3, so in this case, after 1 second, the message would be transferred to 4, and then that's it. So the message will never be transferred to node 1 and 2 because there is no valid node or a valid edge transferring the message from these two nodes. So in this case, we should return a -1, so that it means that there is no possible solution for this problem, or there is no way that all nodes receive the message properly. So this is one of the problem that could be solved by a classic graph algorithm, which is called Dijkstra. So if you don't know what Dijkstra is, the algorithm, I will put a link in the descriptions referring to this algorithm. But for that, we should use a priority queue. So in Python, we can use the built-in class heapQ to keep track of the shortest node that we have in the list. That means at each iteration, we know that what is the a node that can receive the message in sooner than any other node. So at the beginning, definitely at the time 0, the node k is shortest because it has the message at time 0. And then we put the adjacent nodes, in this case 1 and 3, into the queue with value of 1, because these two nodes will be receiving the message after 1 second, and so on. So for that, first of all, we should also keep track of the nodes that they receive a message after any time, because what is important at the end, at the same time that we want to keep track of the time that it takes for the message to be transferred to all nodes, we are also keep tracking of is it possible that all nodes actually receive the message. So for that, so I'm going to use not visited set, so that we know that we have a set of nodes that haven't received the message yet. But in this case, since the nodes are labeled from 1 to n, and Python is a zero-based language, so I'm using 1 to n plus 1. And then after that, we should either use the format that we are given for the graph or use our own format. What I would rather to do is to use other format for keep tracking of the information of a graph. So there are different ways to keep track of the information. What we are given is a list of edges. So for each edge, we have U, UI, VI, and then WI. So the list is given in this format. So we know the starting point, the end point, and the value of that edge, or the time that it takes to the message to be transferred. One other way that some people usually use is to have a 2D matrix of size n by n, and then for each cell in this matrix, so in cell I and j, we can put the value wi, so that we know that there is an edge from node I to node j with the value of wi, or wij in this case. The way that I would rather to use in this case is to have a adjacent list. So for example, in this here in the given graph here, so we have nodes 1, 2, 3, and 4, and then we just put 3 with the value of 1, and then 4, and then 1 with the value of 1, because from 2 we have only 2 neighbors, 3 and 1, and the weight of those edges are 1 and 1. And here, so at node 3 we have 4 and 1, and that's it. So in order to convert this list to what we want, I will define an adjacent list like here. Again, since the labels are one base, so I'm going to use +1 here. So initially, the edges that we have, so for 1, 2, 3 that we just defined, we have an empty list, and then after that we are adding items to that. So for ui, vi, and then wi in the times, I'm just adjacent list ui that append the adjacent index vi and then the weight of that. So this is our adjacent list that we have the information now. And then for the heap queue to implement the Dijkstra algorithm, we can just initially start from an empty list. So by default in Python, the heap queue is a min heap queue. If you know the heap queues, by having only min heap queue, by just negating the key values in the heap, you can implement the max heap queue. And that's why in Python, there's only a min heap queue implemented already, not a max heap queue. But in our case, it is already fine. And in our heap, we are just wanna see at the top of the heap or the peak, we wanna know what is the index of the node that we are going to visit. So initially we are starting from node k, and the time it took to reach that node, and it is 0. But remember, so heap queue is comparing the elements in a list, and in this case we are storing tuples. And in Python, automatically when it is comparing two tuples, two tuples of, for example, k1 and then k2, for example. So since the first elements are equal, then it jumps to the next one and then comparing them based on the second value. But in this case, what matters, we want to store the values in our heap by the time that it took. So I'm swapping them. So we are storing 0 and k in this case, and the heap element format is, so in this case, time and node index. And we are just iterating the heap queue until there is no element remaining in the queue. So while the length of the heap queue is greater than 0, that means we are still having elements in the queue that we are extracting. We are popping an element from the queue and then visiting that. But at the same time, in order to improve the performance, if we have already visited all nodes that we wanted to visit at the first place, we can also stop the program. So the second condition I input here, and the length of not visited is greater than 0. So anytime that we are visiting a node, so initially, for example, in this case, after we visit node 2, you're extracting 2 from our not visited list here, and then so we know how we are just keep tracking the nodes that we haven't visited yet. So as soon as we visit all nodes, we just stop the program. So in order to pop the peak element from the queue, we are using heap queue dot heap pop from the heap queue, and so it just returns this, and then so this is the format that we have. So I'm just removing the parentheses, and then peak time, and then peak index, let's say. Okay, so if the peak node, peak index, in not visited list, so this is the time that we are removing the element from the not visited list. So because we are actually visiting the node at this step. So let's remove that. Not visited, remove peak index, so that after time, in the further time, we know that this node shouldn't be visited yet because it is already visited. And then for now we are using our adjacent list for any adjacent, and the time of adjacent, or the weight of that edge in adjacent list peak index. So when we are visiting a node, now we are looking at what are the neighbor elements and what are the values of reaching to those elements from the current element. If the adjacent not visited, and then we are adding them to the queue. So if we are for a neighbor cell, for a neighbor vertex, if the vertex it is already in the not visited list, we should visit that again. But it is already visited if it is in not visited. So if adjacent in not visited, let's add that to the queue. Heap queue dot heap push to the heap queue, and then with this format. So the time and node index. So the node index for the adjacent is the adjacent itself, and the time it takes is the peak time, the source that we know that it took so far peak time to visit the source, plus the weight of the new node that we are adding. So for example, initially the peak time is 0 because in this example here we are starting from 2, and then when we are extracting that from the heap, so the peak time would be 0, and then we have, in order to visit node 3, we know that it takes the time of adjacent, which is 1, so 0 plus 1 is the 1 second it takes to visit node 3, for example. So in this case we are doing exactly the same. And then we should keep track of the maximum time, because what is asking the problem is to return the maximum time that it takes, so that the message starting from node k be transferred to all other messages. So initially, if we have only one node, so the maximum time is 0 because the message is already there in node k. But otherwise, we are just keep track of the maximum time. So the max time equal to the maximum of the previous maximum time and peak time. Peak time is the time for the current element, because we haven't seen that the current node that we are visiting now, and then we are comparing the time, and then taking the maximum to the maximum time, so that at the end you're just returning max time as the answer. But there's one problem here, which is what happens if there is no way to find, there is no solution, or for if you remember, if we start from node 3 here, we can only visit node 3 and 4, and 1 and 2 could never be visited in this case. So here, before returning the maximum, we are just checking if the length of max time, or if the length of not visited is greater than 0, that means there are some leftover elements in the not visited set that we couldn't visit at all. So just return why is it return -1, otherwise return max time. So that should be fine. So let's try that. Okay, so 4 elements, what happens if you don't have any time? There's no edge. Oh, okay, so it is not a valid one, but let's try the example here. 1. Okay, and the last example, 2 and 2. Okay, let's try that out and submit that. Okay, so that's accepted, and that was everything. So I will put the Dijkstra algorithm link in the description. Don't forget again to, after solving the problem yourself, always check out the other answers proposed in the discussion here, and then compare your running time and then the space time that your algorithm needs with the others, and you can learn a lot from them. Okay, that was everything for today.